All right, welcome back to Math 107. We are at Lecture 12A. In the last tape, we had started Chapter 4, Section 2. What we're in the business of is still creating new functions from old functions. Remember, when you have two functions, if you add them together, you've created a new function. Or subtract, or multiply, or divide, you've created new functions. And in Chapter 4, Section 1, we learned to form compositions of functions, which created a new function from old functions. Well, we're also continuing to create functions, and we're looking at inverses of functions, which are a new function from an old function. Of course, there's some rules and regulations before you can come up with the inverse of a function. All right, yesterday we talked about what is required for a function to be one-to-one. What is that?
Pass the vertical and horizontal.
Okay, pass vertical and horizontal. That is true. It already had to pass the vertical line test to be a function to begin with. So if the question is this function one-to-one? If you already have a function, it's passed the vertical line test. And so to go a step further to determine if it has an inverse, it passes the horizontal line test. So one way of saying it is for each x, there's a unique y that made it a function. And now for each y, there's a unique x that makes it one-to-one. Okay, so in order for a function to have an inverse function, it must first be one-to-one. Must first be one-to-one. And then inverse functions, if you're going to have one, you're interchanging your domains and ranges. The domain of your function becomes the range of the inverse. The range of your function becomes the domain of the inverse. You're interchanging. So I think we looked at an example where you just had a set of ordered pairs that were a function that were one-to-one. So the inverse, we interchanged those. What is the notation we use for inverse function? F with that little -1 of x. Okay, remember that is not equal to 1 over f of x. That is just notation. Notation. Alrighty. Yesterday, I think at the end of class, we had found, we worked on finding algebraically an inverse function. We're going to do one more of those examples. And then we want to be able to verify that two functions are inverses or that they're not inverses. And this is where composition of functions will come back in. All right, then at the end of this lecture, I hope, we have gotten into Chapter 4, Section 3. We're going to start talking about exponential functions, which then leads into logarithmic functions. All right, so let's pick up in Chapter 4, Section 2, finding the inverse of a function algebraically. Let me look back, see which one we did yesterday. Okay, we did an easy one yesterday. Let's do one that's a little more interesting today. Okay, I'm going to just go directly to the book so that you'll have some examples to practice with. And we're going to look for the inverse of a function, and I think I will pick on page 417. Why don't we pick number 58? Maybe that'll be a web-assigned question, and we'll get it done for you. F of x equals 4 over x plus 2. Okay? All right, let's just analyze this function. What is this the graph of? What kind of function is this?
A reciprocal function.
It's what?
A reciprocal function.
A reciprocal, okay, or we can call it a rational function. You could either do reciprocal or rational. The numerator is a polynomial of degree 0. The denominator is a polynomial of degree 1. For the function, what is this domain? What is the domain of this function?
All real numbers except for -2.
Okay, x is an element of all real numbers except x can never be equal to -2. All right, so what is this going to tell me for my inverse function? Is it going to give me the range? Is it going to give me the domain or the range for the inverse function? If the domain of the original function is this, what am I now going to know?
The range.
The range of the inverse function. The range, remember that's y values. The range will be y is an element of R, but y can never equal -2. Okay. What is the range, can you tell me what is the range of this function? Is there a y value this will never be? Think about, what's the horizontal asymptote here? This is a rational function. You know how to find the horizontal asymptote. The degree of the numerator is less than the degree of the denominator. What is the horizontal asymptote? 0. Y equal to 0 is the horizontal asymptote. And if you think about it, 4 over a number can never be equal to 0. 4 over a number can never be 0. So this function can have a y value, everything except for 0. So the range here is y is all real numbers, but y will never be equal to 0. 4 over a number could never be 0. Okay, now what information does that now give me about my inverse function? That x can never be equal to 0. So for my domain, it's going to be all real numbers, but x can never be equal to 0. Alrighty. What we want to do is find the inverse function. Alright, somebody tell me how you know this is already 1 to 1. Can you visualize the graph of this? Yeah. It looks like the graph 1 over x, right? And we know what that looks like. That 4 just means some vertical stretches by a factor of 4. And then that means a horizontal shift to the left of 2. So you already know the graph looks like this. And then you're just going to shift it and stretch. Right? So you know that is 1 to 1 because it's going to pass the horizontal line test. Okay? All right, so yes, it's 1 to 1. And I think your book already tells you that. It says these functions are 1 to 1. But we just wanted to go how we knew. Okay, it passes the horizontal line test. All right, so what is my first step for finding the inverse algebraically? First step, cookbook, what is it? Interchange your x and y. So this x, because you're interchanging domains and range, the x over here becomes the y. And the y value becomes the x, which is interchanging domains and ranges. Excuse me?
Like x doesn't become negative x, or why does it just switch out because it's an inverse?
Right, inverse. We're just interchanging domains and ranges. The old xy's up here becomes the yx's down here. All right, so now our job is to solve for y. Our first step was interchange x and y. Now we're going to solve for y. This is a rational equation. What you going to do, everybody? How do you get rid of the fraction?
Denominator to each side. Multiply the denominator to each side.
Multiply both sides by the common denominator. Okay. Multiply both sides by the common denominator. So we get xy plus 2x equals 4. Just multiply both sides by y plus 2. Yx plus 2x equals, and then the y plus 2's will cancel out over here. All right, so I'm going to try to solve for y, which means that I'm going to leave the term over on the left that has a y in it. So we have xy equals 4 minus 2x. Y is equal to 4 minus 2x over x. And then we'll use proper notation for our inverse function. All right, let's see if our domains and ranges look like they worked out right. If you were looking at this inverse function, wouldn't you agree the domain is that x can't be equal to 0? And if you were asked to find the horizontal asymptote here, the degree of the numerator is 1, the degree of the denominator is 1, your horizontal asymptote is going to be y equal to negative 2, right? The coefficient in front of the leading terms. All right, so your horizontal asymptote is y equals -2. It's never going to touch that. Okay? Everybody good? You may want to talk to me about that. All right, well, we found the inverse for this, but really, how do you verify? Just finding it algebraically or given two functions that somebody claims is inverse is not a proof. How do we verify it? Verify that two functions are inverses. We want to be able to verify that two given functions are inverses. Okay, I have a almost silly illustration, but this is the way it works, and then maybe that will give you some understanding to what it is. All right, right here, this is really silly, but here we go. Here are some clothes that go into a washing machine. Okay. When the clothes come out of the washing machine, we have wet. There were dry clothes that went in. Dry clothes go into a washing machine. Wet clothes go into a dryer. And out on the outside, we're going to get dry clothes. All right, I hope y'all appreciate this great illustration here. I have just illustrated functions that are inverses of each other. One function undoes what the other did to it. The wash machine is your first function. You put your dry clothes into the first function, and it spits out something. You take that and put it in the inverse, and you get back what you started with. Okay? So the way you verify that two functions are inverses of each other, remember you're taking one and putting it inside the other. Does that sound a little bit like composition of functions? You have the composition of your two functions, and what it's going to spit back out is x. It means that you're going to put the inverse function into your function f. They're basically going to cancel each other out, and you get back exactly what you had. There's one more step to that. Both of these have to be true, that you can form the composition either direction, and you get back x. One way is not sufficient to verify. You have to show both directions. When you form the composition, you get back x. All right, so let's take the example we just did. And the first time we're going to do it, we're just going to verify it with numbers. To verify with a particular number doesn't say it's true for everything, but we get the hang of substituting in and see where everything's going. So we want to say given f of x equals 4 over x plus 2, and I'm just going to name this h of x. H of x equals 4 minus 2x over x. All right. We want to find the composition of f and h, and I'm just going to pick a number, 3. All right, now if f and h are indeed inverse functions, when I form this composition, what is my answer going to be? When I find f, the composition of f and h, if f and h are inverses, this is what we just found. If I plug a 3 in, the 3 is going to go in, it's going to do something to it, it's going to put it in the next function, and what's going to be spit out on the other end? The 3, right? If they're inverses, whatever you start out with is what you end up with. All right, let's work it. F evaluated at h of 3. All right. What is h of 3? Okay, so it's 4 minus 6, which is negative 2 over 3, right? 4 4 minus 6 over 3, negative 2/3. And now we're going to substitute negative 2/3 into f. So we have 4 over negative 2/3 plus 2, which is equal to 4 over, if I got a common denominator, that's negative 2/3 plus 6/3, which is equal to 4 over 4/3. And now when you divide by a single fraction, you invert and multiply. And the 4's divide out and you get 3. So because since f and h are inverse functions, basically what happened here was we had 3 got stuck in the h function. That answer got stuck in the f function, and it spit back out 3 on the other side. One function did something to it, the other one reversed what it did, and you came right back out with what you had. Want to ask a question?
No, just wow.
Just wild. Okay. Now, if you think back what I just said, I said one direction is really not enough. It's an and statement. You got to be able to show both directions for inverses. So let's go the other direction. All right, so f of x, I'll rewrite it, is 4 over x plus 2. H of x is 4 minus 2x over x. And this time, let's look at h, the composition of h and f at 3. All right, again, I'm just reversing the order of the composition because by definition, to verify, you have to show both directions. And we did f composition with h before, now we're doing h composition with f. All right, so we have h evaluated at f of 3. All right, what is f of 3?
2/3.
Okay, it looks like it's going to be 4 over 3 plus 2 is 5. Okay, now we're going to evaluate h at 4/5. So we have 4 minus 2 times 4/5 divided by 4/5. 4 minus 8/5 divided by 4/5. Getting a common denominator up in the numerator, 4 is the same thing as what, 20/5 minus 8/5 divided by 4/5. 20 minus 8 is probably 12/5. Divided by 4/5, we'll invert and multiply. The 5's divide out. I have 12 over 4, which is 3. And that's exactly what I expected because they are inverses of each other. All right, using a number is not a proof. That means that you've only shown it true for that one value, 3. So really what we need to do is form the composition with respect to x. All right, before I move on, are we okay, everybody? This far? All right, so let me just make a comment. We've only verified for x equal to 3, not all x. Okay, we only verified for one number. Something might be true for one number, but it may not be true for every number. All right, so I think the book uses verify. We used to call it prove a long time ago. Let me see what your book uses the word verify. Okay, so we want to verify that f of x, which is equal to 4 over x plus 2, and h of x, which is equal to 4 minus 2x over x, are inverse functions. Okay, so this goes along with problems 37 through 46 in your textbook on page 47. I'll write a little note here. This is like numbers 37 through 46, page 417 in your book. Okay? Alrighty. So if we're going to verify, that would mean that if we form the composition of F and H at X, I should get an X back. And if I form the composition H and F at X, I get an X back. And when I do, then I know that these are indeed inverse functions. Okay? All right, I hope you're listening to the instructions to the problem. To start with, we found an inverse algebraically. It meant solve for an inverse. This is basically saying, given these two functions, prove that they are. And the way that you prove, you have to go with your theorem to prove. Okay, it doesn't mean you just go algebraically find it and say there it is. This is the proof. All right, so let's go with it. F evaluated at h of x. This way I'm using all values for x, not just that number. So this is F evaluated at 4 minus 2x over x. Anybody notice where the 4 minus 2x over x is coming from? That's what h of x is. And now I'm going to evaluate f at this number. So that would be 4 over, and where I have an x and f, I'm going to put 4 minus 2x over x plus 2. Is that good? All right, we need to go to common denominator down in the denominator. So this needs to be x over x. So I have a common denominator. So in the numerator I have 4. The denominator is over x. I have 4 minus 2x plus 2x, which is 4, because the negative 2x plus 2x is 0. And then I'm just going to invert and multiply. The 4's divide out, and I get x. Okay? So that's the first part of that theorem that says if you form this composition, this direction, whatever you start with, you stick it in the function, in this case h, it changes the appearance, you put it in f, and it gives you back what you started with, namely x. All right?
What was that? 4 over 4x.
4, when I added in the denominator, that simplified. 4 minus 2x plus 2x is 4 over x. So when you say 4 divided by 4 over x, you invert and multiply.
Mm-hmm.
Was that your question?
Yeah. So that's times x over
4.
4.
Yeah, when I inverted and multiplied, I had x over 4. 4 is divided out and left me at x. Is that good? Thank you. All right, so that was step 1 for verifying. One direction's not enough, got to go both directions. So we have now h evaluated at f of x, which is going to be h evaluated at 4 over x plus 2, which tells me I need to go to the next. Let's do a blue sheet underneath so I don't have to flip the page. All right, so my f of x is 4 over x plus 2. Now I'm going to put 4 over x plus 2 back into h, right here. So this will give me 4 minus 2, and in the place of x, I'll put 4 over x plus 2 divided by x. Let me just slide this down. In my h of x, where I had an x, Oops, I forgot to do that, didn't I? This would have to be, sorry, 4 over x plus 2. All right, it's getting sloppy. Let's try again. F of x equals 4 over x plus 2. H of x is equal to 4 minus 2x over x. We're looking at h evaluated at f of x, which is h evaluated at 4 over x plus 2. All right, let's just do it from here. So where you have x in h, you're going to replace that entire fraction there for the x's. So we will have 4 minus 2, and in the place of the x, we write 4 over x plus 2 divided by 4 over x plus 2. By the way, if you noticed, I almost made a mistake and put the x there. I have seen on so many tests where people forget to substitute for every location of x, and I was just about to do that myself. So mark yourself a little red mark in your notes so you don't forget. All right, let's see what we have here. So we have 4 minus 8 over x plus 2 divided by 4 over x plus 2. Negative 2 times 4, negative 8. Okay, what kind of fraction is this called? Again? Complex. So we need to get a common denominator up here. X plus 2 over x plus 2. So this will be equal to 4 times x plus 2, which is 4x plus 8. Then we got a minus 8 all over x plus 2. 4 times x times 4 times 2 divided by 4 over x plus 2. Of course, 8 minus 8 cancels out. And now we have 4x over x plus 2. 4x over x plus 2, and we're going to invert and multiply. Invert and multiply. And you see the factors x plus 2 divides out, the 4's divide out, and we're left with x. Okay? So we have verified inverse functions. Everybody good? All right, I think what we want to do is just flip through the pages of the book and make sure we got all the theorems and definitions, and make sure everything's good for section 4.2. 4.2. All right, I'm on page 404. Determine whether a function is one-to-one. We know how to do that, correct? Determine if the inverse of a function defined by an ordered pair. Remember, you just interchange your x and y values. Get the graph of an inverse function from the graph of a function. Did we do one of those? We'll do one in the exercises. You just take your points and interchange. And find the inverse of a function defined by an equation. All right, flipping through the pages. I'm on page 405. Where it defined one-to-one. Over in the margin, it tells you in words a function is not one-to-one if two different inputs, x values, correspond to the same y values. Input is domains, outputs are range. Inputs are x's, outputs are y's. Okay? On page 406 is your horizontal line test. I think everybody's got that for determining if a function has an inverse. I know I said this in the last video. A function that is always increasing over its interval, that's over its domain, is one-to-one. So if it's always increasing, it's not going to turn around, so therefore it's got to pass the horizontal line test. And when that's decreasing on an interval, over its domain, is also one-to-one. So if it's coming down, there's no way it's going to turn back up to make it not one-to-one. Okay, objective 2 was just saying if you have a set of ordered pairs. I think we looked at an example in the last tape. Example 4 is right here, where you just have an ordered pair. So to find the inverse, you're just going to interchange your x and y values, which is to illustrate the idea that the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. And over in the margin on 408 is your warning for your notation. F to the -1 is a symbol for inverse function. It is not an exponent. Be sure that, I see that often happen on tests. People start to confuse it with a negative exponent. Okay, then top of page 409 is what we were just doing. The way you verify that functions are inverses of each other is that you form the composition both directions and you get back your x. The way you verify, you form the composition both directions. And you've got some examples in your book. Okay, flipping over, we'll do one of these problems in the exercises, but basically what they were trying to tell you was if you have the graph of f, then to graph the inverse, you're just interchanging your x and y's. And what happens when you do that is it's just a reflection across the line y equals to x. Okay, so to graph it, you just interchange your x and y and flip it across the line y equals x. Objective 4 was finding your inverse algebraically, just like we did, interchanging x and y, solve for y, use your proper notation. Okay, and I think that is it, except that we do want to do one graph. So let's just do one in my book together. We'll pick number 32. We want to graph the inverse of this function. All right, so I'll just use a green pen. If the point 2 1/2 is on the function, what's on the inverse?
1/2,
1/2, 2. So that would be right there. It's just going to be a reflection. And a reflection just means if you fold the paper along the line y equals x, it would fit on top of it, and actually that makes a perpendicular line from across those two. If you touch one to the other, it'd be perpendicular to the line y equals x. Okay, instead of the point 1, 0, we would have the point 0, 1. So I'll just connect the dots there. And instead of the point 0, -1, now we have -1, 0. Just connect the dots. And instead of the point -2, -2, we have the point -2, -2. So that's already on the line y equals x, so we will connect the dots. Of course, I would label those, except my pen is so big. Maybe I should. 1/2, 2. And that one is 0, 1. And that one is -1, 0, and then that one. And there's your inverse function. Pretty easy, huh? Everybody got it? All right, great. We're going to move on into Chapter 4, Section 3. You have lots of homework problems on inverse function. And all of this, again, was just really building up so that we could talk about exponential and log functions, because exponential functions and logarithmic functions are inverses of each other. Exponential functions, logarithmic functions are inverse functions. They're inverses of each other. Exponential functions. All right, let's look at page 419 at our objectives for this chapter. We want to be able to evaluate exponential functions, meaning plug and chug, evaluate some exponential functions. We want to be able to quickly graph exponential functions, so we'll have our transformations. We want to define the number e. E is an irrational number. Who can already tell me what e is approximately equal to?
Like 2.17 or something.
Okay, e is a number that's approximately equal to 2.17. Is it 2.17 or 2.71?
2.71.
Okay, 2.71. Okay, E is a number. It's about 2.71. It is one of those irrational numbers like pi. The decimals never repeat, never terminate. And then we want to practice solving some exponential equations. Okay, so the first thing we want to do is go to the end of chapter, this section, 4.3, and look at Are You Prepared? And I'm only going to pick one problem out of here for you to do, and that is problem number 1. Problem number 1. Let's see if we can focus in on that a little bit. You are asked to simplify 4 cubed, 8 to the 2/3, and 3 to the negative 2. Just simplify that without a calculator. Simplify. Talk to your neighbors about it. Okay, you guys are going to be the expert on 4 cubed. Y'all are going to be the expert on 8 to the 2/3, and y'all are the expert on 3 to the negative 2. Okay. Okay. I forgot. Are you guys the expert on 4 cubed? All right. What does 4 cubed mean?
4 times
4 times 4 times 4, and that is 64. Check.
3 over. So it'd be 1 over 3.
Okay.
So it's 9.
8 to the 2/3. What does that mean? How are you dealing with 8 to the 2/3?
8 times 2/3 of itself.
What is it?
You just take the cube root of 8 and then square it.
It means the cube root of 8 squared. A to the m over n, where m over n is reduced to lowest terms, means you're going to do the nth root of a and raise it to the m, or it could actually be the nth root of a raised to the m. Usually it's easier if you do the nth root of a and then raise it to the m. All right, cube root of 8 is what?
2.
2, because 2 cubed is 8, and then we're going to square that, and we get 4. Okay? What would be 16 to the 3/4 power? It would mean the 4th root of 16, and then we cube it. What's the 4th root of 16?
2.
2, because 2 times 2 times 2 times 2 is 16. 2 cubed, and we get 8. Everybody remember this? What is the negative 27 to the 1/3 power equal to?
Third.
What can you multiply times itself 3 times to give you negative 27?
3.
Negative 3.
Negative.
Means cube root, negative 27, negative 3. Okay, need to go back to pages 20 to 21 and 71 to 73 if you're missing that. Very important, not only for this course, but for your calculus course. Okay, we got one more. From the book, 3 to the negative 2 power. What does that mean?
Flip it over and square it.
It means take the reciprocal and square it, doesn't it? And we get 1/9. Okay, what is minus 3 to the negative 2? 1/9? How many say 1/9? Who doesn't agree?
I don't know. It's something. I can't remember. It's something, but it's something wrong.
This is it.
Okay,
What was next?
I'm going to do versus. What's the difference between these two problems?
One's in parentheses, so it multiply the negative squared and it'd be positive.
Exactly. When it's parentheses, this will be 1 over -3 squared, which is equal to positive 1/9. Without the parentheses, the exponent only goes with what it's next to. This is like -1 times 3 to the -2. So it's -1 times 1 over 3 squared, and you get -1/9. Be careful about that. You knew something was wrong, didn't you? All right. Let's review our properties of exponents from long ago. Properties of exponents. And I'll just do it with some examples. Suppose I have 2 cubed times 2 to the 4th. The bases are the same, so you add the exponents. 2 to the 7th power. Bases are the same, add the exponents. What about if you have 2 cubed divided by 2 to the 4th? Okay, you're going to subtract them, so what's it going to end up with? 3 factors of 2 are going to divide out in the denominator, and you're left with 1 factor in the denominator. 4 minus 3. What about 2 to the 4th over 2 cubed? What's that going to be? 2 to the 1st, right. Okay, what about 2 cubed raised to the 4th power?
It would be 8 to the 4th.
Well, it would be a 8 to the 4th, but I want to keep the base 2
Oh,
because I'm illustrating the properties of exponents. What do you do for power of a power?
is that when you multiply?
You multiply to the 12th. Because this really means that you're saying 2 cubed times 2 cubed times 2 cubed times 2 cubed, right? 2 to the 4th, 2 cubed to the 4th means you're multiplying 2 cubed times itself 4 times, so there's 3, 6, 9, 12. That's why you power of a power. Use power of a power. Everybody good? Questions? Okay, watch out for minus with a number raised to a negative power. Everybody good? Okay. So now we are prepared for section 4.3. And I'd like to say, so far, we have worked with the power functions, really some algebraic polynomial functions, but basically we had y equals x raised to a power. And the deal was that x is the variable and a is a constant. That's what we've studied so far, such as y equals x to the 5th. Okay? But now we want to talk about an exponential function. Exponential function. And that will be of the form y equals a raised to the x. And the exponent now is the variable, and the base is the constant with a few restrictions. That constant is that a has to be greater than 0 and a not equal to 1 in order for it to be an exponential function. All right? So it seems like it takes students a long time, and that's why I make a big deal about this, to recognize that in the past we had a variable raised to a constant power. Now we have a constant raised to a variable power. All right, so let's start with a really simple one for exponential functions. What grows exponentially? What are some things that grow exponentially anyway?
Bacteria.
Bacteria, multiply, it divides, keeps multiplying. What else grows exponentially? What?
An egg cell, like an embryo.
An embryo? Yeah, those cells multiply and divide.
Population.
Population growth. How about money in a savings account earning compound interest? Grows exponentially. What decays exponentially? Goes down.
Radiation.
Radiation, radioactive substances, right? They have like half-lives. What else goes down?
Why?
Can't think of anything else that goes down? Well, it could be a town where everybody's moving out because there's no industry coming in. Anything where you're starting to go down. Or the way my investing in the stock market did, that's another example of going down. There you go. All right. What we want to do is graph a simple exponential function. We're going to graph y equals 2 raised to the x. This is an exponential function. The base is a constant. The exponent is a variable. Okay? All right. What would you say is the domain for this function? Can I raise 2 to any power?
Yeah.
Can I raise 2 to the square root 3 power? I can with a calculator, right? I can put x as any real number. What's 2 to the 0?
1.
1. What's 2 to the negative 1?
1.
1/2. Okay, so I can raise 2 to any power, especially if I have a calculator, and get its value. All right, what do you think the range is? If I raise 2 to some power, am I going to ever get a negative number? No. Will I ever get 2 to some power equal to 0?
No. Well,
No. But it can get pretty close to 0. For example, if I have 2 to the negative 5 power, that's 1 over 32. So my range is going to be y is greater than 0. All right, let's just plot a few points and get a visual on this one. All right, so we'll plot a few points, see what's happening. We'll pick -2, -1, 0, 1, 2. I'll start the other way. 2 squared is 4. 2 to the first is 2. 2 to the 0 is 1. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. Okay, -2 1/4 is somewhere right here. -1/2 is somewhere right here. 0, 1, 1, 2, 2, 4, and of course 2 cubed is 8, and the graph's going to go like this and start to come down like this. Okay. Let's answer a couple questions from the graph. I'm going to use the word limits. What's the limit as x approaches infinity of 2 raised to the x? As x gets really, really big, what is the y value getting close to? Everybody just says infinity. What about the limit as x approaches negative infinity of 2 to the x? Where's this thing getting closer and closer to? 0. Recalling the definition of horizontal asymptotes. Horizontal asymptote. As x gets really, really big, or if x gets really, really small, if the y value starts to approach a number, y equal to that number is the horizontal asymptote. So does this curve have a horizontal asymptote?
yes.
Yes. The horizontal asymptote is what? What's the equation?
Y equals 0.
Y equal to 0. Okay, it doesn't have to approach going to infinity or negative infinity. The word is or, not both, but or. So y equal to 0 is the horizontal asymptote. Okay? All right, let's just do some words on sketching, and we won't actually graph them unless you beg for this. Suppose you were asked to graph y equals 2 to the x minus 3. Y equals 2 to the x minus 3. How's that going to compare to y equals 2 to the x?
Shift it down.
It's going to go down 3. What is the equation for the horizontal asymptote?
Y equals -3.
Y equals -3. How do you know that so fast?
Because when you shift down, you shift the asymptotes with it.
Exactly. When you had y equals 2 to the x, if your horizontal asymptote is y equal to 0, if you're going to do a vertical shift down of 3, your asymptote is also going to come down 3. Okay, is that good? All right. What about y equals 2 to the x plus 7? Y raised to the 2 raised to the x plus 7. What's that going to do?
Shift up 7.
Is it a shift up of 7?
Shift up.
It's a horizontal.
No.
Is it vertical? What is it?
Horizontal.
Horizontal. Shift. Which way? Left.
7.
7. Give me the equation for the horizontal asymptote.
Y equals 0.
Y equals what?
0.
It's still 0.
Y equals 0, because it's really the graph of y equals 2 to the x, and all you've done is shift it to the left 7. You haven't affected the asymptote. Okay? All right, last one. Y equals 2 raised to the x minus 3, and then a plus 12. Okay, it's going to be a horizontal shift right 3, so we're going to send it to the right 3, and a vertical shift up 12. Can you give me the equation for the horizontal asymptote?
Y equals 12.
Y equals 12. Everybody got it? All right, so we're good with y equals 2 to the x. Now, I want you to tell me what you think the graph of, let's do that in red, y equals 3 to the x is going to look like. Y equals 3 to the x.
Gonna go up steeper.
And let's just put it here. Y equals 3 to the x. Green is y equals 2 to the x. All right, let's just plot some points. When x is 2, the y value is 9. When x is 1, the y value is 3. When x is 0, the y value is still 1. When x is -1, it's a third. X is -2, it's a ninth. Okay? So when x is 2, the y value is 9 way up here. When x is 1, the y value is 3. And when x is 0, the y value is 1. So it's going to go up a lot faster. Okay, but let's see what happens when x is less than 0. When x is -1, we are now at a third as opposed to a half. And when x is -2, we're down here at a ninth as opposed to a fourth. So it's going to still have almost the same shape, but when x is bigger than 0, it's going to go up faster. And when x is less than 0, it's going to approach the
X-axis.
x-axis a lot quicker. Does everybody see that?
Mm-hmm.
All right, so without much effort, what's the graph of y equal 5 to the x look like in general?
8 goes up.
It's going to do the same thing, but it's going to go up a lot faster when x is bigger than 0, and then it's going to get closer to the x-axis as x is less than 0. All right, everybody good? All right, so the basic rule is this. If we have y equals a raised to the x, and a is a big number bigger than 1, strictly bigger than 1, your graph is going to always look something like this, just to give you a visual. Okay? It's going to always be increasing. It's going to always go through what point here?
0, 1.
0, 1. Okay, so your graph, as long as a, we only looked at a bigger than 1 when I did numbers 2, 3, and 5. In the beginning of the next tape, we're going to look at where a is a number between 0 and 1. Okay? All right. That's great for today, and we'll pick up with this next time. Ooh, that sounds yummy. Alrighty, we are ready to start back. And if you heard us before we stopped talking, we were talking about food because it is close to the lunch hour right now. Alright, we're in lecture. Everybody ready? Hard to get off that food topic. Everybody ready? Lecture 12B. We were working on exponential functions, chapter 4, section 3. This is where your test 2 ends. And I expect that we will finish that and begin talking about your test 2, answering questions, trying to get caught up. For sure, lecture 13A, specific questions, getting ready for your test. All right, at the end of lecture 12A, we had just looked at, I'll just rewrite it. We had just looked at the graph of y equals a raised to the x when a was bigger than 0. These are, a bigger than 1. We were looking at 2 to the x, 3 to the x, 4 to the x. And the interesting thing is they all go through the point 0, 1. It grows, has a horizontal asymptote, y equal to 0. We call this a growth curve. Growth. It's growing exponentially. All right, we want to, and we said, you know, the bigger the a is, the quicker it rises when x is bigger than 0, and when x is less than 0, it falls a lot faster. I want to just back up, though, and look at the graph of y equals 2 to the x and 3 to the x right here. Because there's a special number between y equals 2 to the x and y equals 3 to the x, and that special function is y equals e to the x. Y equals e to the x. Y equals e to the x is going to fall right between, not exactly halfway between though, y equals 2 to the x and y equals 3 to the x. Y equals e to the x. And y equals e to the x is called the natural exponential function. Most physical problems will take on their simplest form with base e. And when you work with base e, once you get in the calculus for derivatives and integration, it's going to be a piece of cake. So most people, when they have some kind of model and it's to a base 2 or 3 or 10 or any other base, will actually convert it to a base e. And we'll learn how to do that. I think that's in chapter 4, section 6, when we learn to convert from one base to base e. But this is the simplest form of base e that you can get your exponential function in. Now, we have a definition for e. E is defined to be This is the definition of E. E is defined to be the limit as n approaches infinity of 1 plus 1 over n raised to the nth power. Well, that just means, and your book went through and set up a little chart. I'm going to show that to you. It's on page 427 in your book, 427. They pick n to be 1, 2, 3, just getting bigger and bigger. Remember, we were looking at the limit as n approached infinity, so we got all the way to, looks like a billion. There's a million, billion, okay. And they substituted into each part of the expression and raised it to the nth power. And as n got really, really big, this expression gets real close to 2.718281827. Of course, if you kept going, you would see that the decimal is not going to terminate, it's not going to repeat. But this is the definition of E, and we usually just say that E is approximately 2.71, or 2.72 is actually where it rounds better. Okay, most of the time we just go E is about 2.7. So you would know then that when you graph y equals e to the x, it would have to fall between y equals 2 to the x and y equals 3 to the x, because that number falls right in between. Okay, so when you see y equals e to the x, that is called a natural exponential function. So if you were going to ask this question, e, which is approximately 2.72, if you were asked, given the natural exponential function y equals e to the x, state the domain, range, asymptote. What would you say the domain is? Y equals e to the x? Very quickly. That was easy. That's not a trick question. What's the domain? All real numbers. Let's go to the calculator and just plug in some numbers. Can you see it? Okay, the E button is right above the natural log, and that's because natural exponential and natural logs are inverse functions, and we'll be studying natural log next section, I think, of the book. All right, so if I wanted to raise e to the 5th power, e raised to the 5th, this is really about 2.72 raised to the 5th, and it looks like we have 148.41. I could raise e to the pi power, so that's e raised to the 3.14. Remember, x is my exponent, and it can be any real number. That's about 23. I could raise e to the negative 15. And that comes out to be 3.059 times 10 to the negative 7. So that's a pretty small number. That's 1 over like 2.7 raised to the 15th. So that's a very small number. That little e to the minus 7 means move your decimal 7 places to the left. All right, and of course, e to the 0, you already know what that is. E to the 0 is 1. E to the 0. Okay, so you've got all real numbers. What is your range, everybody? You know the graph's going to look just like this, because e is a number that's about 2.7. What's your range?
Y equals greater than
Y is greater than 0. What's your asymptote?
Y equals 0.
Y equal to 0. Y equal to 0. Okay, so e fits this category right here, because e is a number bigger than 1. All right? Everybody say it. Natural exponential function. Natural exponential function. Whenever you have base e, it's called the natural exponential function. Okay, let's look at y equals a to the x when a is between 0 and 1. Let's look at the exponential function when a is between 0 and 1. We'll just take an example. This would be something like y equals 1/2 raised to the x. Y equals 1/2 raised to the x. All right, we'll plot some points. x, y. We'll go -2, -1, 0, 1, 2. Okay. What's your domain, by the way? All real numbers. What about your range? 1/2 raised to some power. Can that ever come out to be negative? 1/2 raised to some power. What about, could it ever come out to be 0? 1/2 raised to something, that ever give you a 0? All right, but if you raise a 1/2 to a positive power, you got a positive number. So your range is going to be y is greater than 0. All right, let's do some evaluating. Let's start with the 2. 1/2 squared is a 1/4. So we have the point 2, 1/4. 1/2 to the first is a 1/2. 1/2 to the 0 is 1. What is 1/2 raised to the -1 power? 1/2 raised to the -1 power?
1/1.
You just take your reciprocal, right? So the reciprocal of a 1/2 is 2. So when x is -1, the y value is 2. And then what about 1/2 to the -2? That's the same thing as 2 squared, which is 4. Okay, do you see what the graph's going to look like? It's going to go like this. Okay? As opposed to the growth, we call this one a decay function. Decay. It's always decreasing where the growth was always increasing. All right. What is the limit as x approaches infinity of 1/2 to the x? As x gets really big, where's this thing going? It's going towards 0. That immediately tells you an asymptote. What is the asymptote? Y equal to 0. What about, what is the limit as x approaches negative infinity? As x is going to negative infinity, where's this thing going?
Negative infinity. I mean,
Positive infinity. As x gets really, really small, this curve's going to fly off in the direction of positive infinity. Okay, because as x goes to infinity, the y value gets very close to 0. Y equal to 0 is a horizontal asymptote. Okay, everybody good? All right, so let's just generalize. I mean, I know that we've done so many transformations, you would know how to shift these all around. Okay, so let's just generalize. Oh, well, let's just read out the book. It's all organized for us right here. Okay, I'm on page 424 at the top. I hope you're wearing out your textbook. You paid a lot for it. You need to wear it out. Top of page 424. Properties of the exponential function. Remember the first examples we looked at were when the a was bigger than 1, a to the x. Your domain is all real. The range is all positive numbers. That means y is greater than 0. Your y-intercept is at 1. Y equal to 0 is the horizontal asymptote. And they wanted to talk about this function is increasing. And they also mentioned it's 1-to-1. And that's getting you ready to know, since it's 1-to-1, it must have an inverse function. Okay? And it contains the point 0, 1, 1a, -1, 1 over a. All right, that was our growth curve. And the example we just now looked at is on page 425. 425 at the bottom. This is when your a was between 0 and 1. You still had the domain all real numbers. Your range is all values greater than 0, positive numbers. The y-intercept still goes through 0, 1. The x-axis is still your horizontal asymptote. This function is decreasing. We called it a decay function. We didn't mention that it was 1-to-1, but again, this is getting you ready to talk about inverses. This will also go through the point 0, 1, and it is continuous and smooth. Okay? Everybody good? Alrighty. I think that we are doing fine in section 4.3. So the next thing we want to talk about now are solving exponential equations. So we're on objective 4. Objective 4. Solving exponential equations. Now, this is not the only way to solve exponential equations, but in this particular section, the key thing is we're going to have like bases. Okay, when we get over in chapter 4, section 6, I believe it is, we will look where we have unlike bases. So this is just going to work for when we have like bases. And our rule, which is on page 428, says when we have exponential equations equal to each other, and notice it has like bases, a to the u equals a to the v. So if we have exponential expressions, and it's an equation, so we got an equal sign, if the bases are the same when we have an equation, then common sense tells you, well, the exponents must be equal. If the bases are the same, the exponents are equal. All right. So let's just take an example or two, and then we'll go to some of the exercises in the back of the book. So the rule is a to the u equals a to the v. Notice that's like bases. Then u equals v. All right, simple example. 2 to the x equals 8. All right. If I'm trying to apply this rule, I need the bases to be the same. So would it be easier to get the 2 to a base 8 or the 8 to a base 2?
8 to the base 2.
Yeah, so we just write that 2 to the x equals 2 cubed. 2 cubed is 8, so we're looking to see if we can get the same base, and it's usually a prime number for your base. So now the rule says if the bases are the same, then the exponents are equal. So we know 2 cubed is 8. All right, see how that works? Okay, well that one's too easy, so we want to do some problems where you have to use your properties of exponents. All right, so I decided to, let's just head to the exercises, page 432, and I'm going to pick a problem such as, where is a good one? I'm going to pick number 57. This is on page 432. 8 to the x squared minus 2x equals a half. And our instructions are to solve for x. Okay, so when you're going to solve an equation like this, you're going to try to get a base, and usually your base is a nice little prime number of some sort. So if you're looking at 8s and 2s, what automatically are you going to use for your base? If you think 8s and 2s, 2 would be a good one. All right, so how would I rewrite 2 to some power that gives me a half? Negative 1. 2 to the negative first. All right, how do I rewrite 2 to some power that gives me 8? 2 cubed. 2 times 2 times 2. All right, so first we had to find a common base. Okay, so I saw 8s and 2, so I realized the common base is 2. All right, now the job is to solve here for x. And over on the left side, I have 2 cubed raised to the x squared minus 2x. So I have to use my properties of exponents. A raised to the m to the n. What do you do with those exponents? You multiply. So this is 2 to the 3x squared minus 6x equals 2 to the negative 1. Okay, I'm just going to power of a power, I'll multiply those exponents. All right. So you got to know remember all your properties of exponents here. So now I can use the rule, the bases are the same, so I set the exponents equal. The bases are the same, so I set the exponents equal. Okay, what kind of equation do I have here? Quadratic equation. So what's my first step in solving a quadratic equation?
0 on one side.
Yep, have to have a 0 on one side. Okay. Is that going to factor? I don't see that it's going to factor easily. So how are we going to solve? Go to our quadratic formula. So x then is equal to, remember a is 3, b is negative 6, and c is 1. So x is 6 plus or minus square root of negative 6 squared is 36 minus 4 times 3 times 1 is 12 over 2 times 3, which is 6. So we get 6 plus or minus the square root of, what's that, 24? 24 over 6. So what happens is I have two real solutions. I couldn't factor with the set of integers, and you could just plug and chug away on your calculator if you wanted to get a little bit better, but one value for x that satisfies this is 6 plus the square root of 24 over 6, and the other value is 6 minus the square root of 24 over 6. Two values for x. Okay? Meaning that if you put them back up here, raise 8 to that power, that would be equal to a half. Everybody good? Okay, let's try another example. I'll hold that there a second. I'm going to jump on problem number 65. Still on 432, and I'm going to look at problem number 65. Page 432, number 65. Okay, we're still solving for x. So we have e to the x squared equals e to the 3x, parentheses, times 1 over e squared. Okay, remember e is that number that's about, what, 2.72? So we have e to the x squared equals e to the 3x times 1 over e squared. All right, I need some suggestions on how we're going to start solving for x. What do I need to do over on the right side?
Change the 1 over e squared to e to negative 2.
Okay, all right, so you're going to look for a way to simplify this. So you're going to write that as e to the 3x times e to the negative 2, because we're trying to get the single base e here. Okay, now what do your properties of exponents say you can do?
If you have like bases, then you can add the extra.
Like bases you can add, so you got e to the 3x minus 2. All right, good. So now we have e to the x squared equals e to the 3x minus 2. All right, so now the bases are the same, base e. Therefore, x squared must be equal to 3x minus 2. another quadratic equation. So x squared minus 3x plus 2 equals 0. And when we factor, we'll get x minus 2, x minus 1. X equals 2, or x is equal to 1. Suppose we want to check this. Let's check and see. Where do I plug in 2? Do I plug it in right here? Which step do I plug it in? Where do I substitute the 2 in?
Would it be like step x squared equals 3x minus 2?
Okay, anytime you're going to check an answer,
Like in the beginning.
you always go back to the original problem before you started simplifying and playing with it. So for our check, we want to know is e raised to the 2 squared, is that equal to e to the 3 times 2 times 1 over e squared? Okay, so if you have e squared squared, e squared squared, you will get what? E to the 4th. Okay? And here you have e, 3 times 2 is 6, e to the 6 times 1 over e squared. So e to the 6 divided by e squared is e to the 4th. So you know x squared checks. All right, let's try 1. Is e to the 1st squared equal to e cubed times 1 over e squared? Well, e to the 1st squared, 1 squared is 1, so that's e to the 1st. And then e cubed divided by e squared is e to the 1st. Check. Okay, so you always check going back to your original problem. Everybody good? All right, so when you're solving exponential equations, you're going to have to remember your properties of exponents. You have to simplify using your properties of exponents, get your like bases, and then set the exponents equal. Everybody good? All right, let's look at problem number 72. Problem number 72 is the graph. Let's see if we can, there you go. Our instructions are to write the equation for this curve. Write the equation for this exponential function. All right, now it goes through 0, 1, and the point 1, 5 is on the graph, but we're told that it's an exponential function. All right, let's see if you can tell me how you do this. The basic curve, the basic function is what? Y equals a to the x. Do we know if a is bigger than 1 or between 0 and 1?
Bigger than.
A's got to be bigger than 1 because it's growth, right? All right, so our job is going to be to figure out what the a is. How are you going to figure out what a is from this graph?
Plug in your point.
Just plug and chug. You're exactly right. Let's pick the number 1, 5. When x is 1, y is 5. So 5 is equal to, I know that y'all think this is too easy, 5 is equal to a, right? So we found it. Therefore, this graph is y equals 5 raised to the x. It looked worse than what it was, didn't it? Double check it. Check your other point, negative 1, 1/5. If x is negative 1, you would get 5 to the negative 1, which means 1/5. All right, so that was pretty easy to find, wasn't it? The deal was you had to recognize the basic formula, y equals a to the x. And then you did the exact right thing. You put a point in that was given on the curve, and you were able to solve for the a.
Did you do number 74?
Let's do number 74. Thank you for asking. Good. Number 74. Start out with your basic. Y equals a to the x. Y equals a to the x. All right, now, you see some e's in here, so that's going to help you. See some e's, but we can do just like we did before. Can't we just pick a point like 1 negative e? Pick a point like 1 negative e. So y is negative e when a is raised to the first power. Right? The point 1 negative e is a nice easy one to put in. Y is negative e when x is 1. So do we know what a is right away?
Negative e.
Looks like a is going to be minus e. So let's see. It looks like it's y equals minus e to the x. Let's just check some points. Now notice that there's not parentheses with the minus e, and you know there wouldn't be parentheses because all the y values are negative. So it's got to be a reflection about the x-axis. Let's just double check it. When x is 2, I'm just checking that point. When x is 2, the y value is minus e squared. Check. Do you see that? And when x is negative 1, that means take the reciprocal, and you get negative 1 over e. So those points check. All right? So the instructions and the problems look worse than what it is. They're just trying to drive home to you that an exponential function is of the form y equals a to the x. All right? Everybody good? Okay, let's flip through the pages and make sure we've covered everything. I think we have in 4.3. And then I'll start answering questions. Okay, at the bottom of page 419, there we're just wanting you to practice plugging in your calculator. 2 raised to a power. I'm sure everybody has one of these little arrow buttons right here on your calculator somewhere for raising to a power. Or and some calculators have a little YX button. All right, so play around with your calculator to make sure that you can plug and chug. On page 420, this is a reminder of your properties of exponents. They call them laws of exponents. Laws of exponents, a review. There's your little negative exponent right there. Power of a power. Bases are the same, add. Then an exponential function was defined for you. A base greater than 0, not equal to 1. A constant greater than 0, not equal to 1, raised to a variable power. Okay, and let's flip through. 421 is where there's just sketching some graphs. The graph y equals 2 to the x like we did. On page 424 and 425, we've already looked at those summaries for sketching. Bottom of page 426. Page 426 is your definition of E. It's a limit as n goes to infinity, 1 plus 1 over n raised to the n. Just in case you're wondering, no, you do not have to memorize that. The book just wants you to know that it didn't fall out of the sky. It really came from somewhere. What you need to remember that is that E is about 2.72. Okay, it's about 2.72. Okay, again, you don't have to memorize that at all. Of course, if you want to, go for it. Top of page 426, they were doing some transformations for you, some transformations of your graph. This was a graph of 2 to the minus x. You could write that as 1/2 to the x. That's how you got your decreasing function. 2 to the minus x is the same thing as 1/2 raised to the x. So you could look at your decreasing function and then just shift it down 3. Okay? And what else? And then solving exponential equations. And we are done. Everybody's good. All right, any questions from that? All right, let's talk about questions you have about your upcoming test. Where does it start?
3-2.
3-2? I actually forgot, that's why I was asking. Test 2 begins chapter 4.3 section 2. Is that correct? And it goes through 4.3, and what else is in there?
Bounds.
Calculated factor.
Oh, calculus factoring.
Factoring, calculus-related factoring. Calculus-related factoring.
Is it that sheet you gave us?
The sheet I gave you, and also after I discovered it was also in the review section of your textbook. I think it was about page 53 if my memory is any good. Now I'm curious. Is it page 53? Yes. Page 53 were some extra problems on that, besides the sheet I gave you. Alrighty, let me take a question and we'll spend the rest of the time today on that, and then I'll see what other questions you have tomorrow. Give me a question, somebody, that you have.
Can you do it for identifying polynomial functions and their degree?
Okay, question is about how do you recognize a polynomial function and the degree. Okay, it probably is easiest by just using some examples of what is and what is not a polynomial function. So I'm just going to give you two examples here. 3x to the fifth plus 2x squared minus 1 versus y equals 1 over 3x to the fifth plus 2x squared minus 1. One of those is a polynomial function and one is not. Which is?
The bottom one? No.
They're both on the bottom.
Oh, I'm sorry.
Which one's a polynomial function?
The second one.
What makes a polynomial function?
The degree on top has to be less than the degrees on bottom.
You're on rational functions.
Non-negative.
Non-negative integer exponents. Can't have any negative integer exponents. Which is the one is a polynomial? If I rewrote this one, this is going to be a 3x to the fifth plus 2x squared minus 1 to a negative 1 power. Which one's a polynomial?
First one.
First one. What kind of function is this? Because it's a fraction. What's it called? Rational. Rational is your fraction. What is the degree of this polynomial function? 5. What's the leading coefficient?
3.
How many zeros might I have?
5.
5.
At most 5.
At most 5. Could I have 4?
Yeah.
3.
Yeah.
2.
Yes.
1.
Yes.
0.
Yes.
No.
No. No.
It's not.
No. No.
I do that.
No.
Why do I have to have at least one real?
It's
It's odd number.
It's an odd power, so it's got to go through the x-axis. Okay, if it were even number, I might be able to get away with no real zeros. All right, so a polynomial function is going to have positive integer exponents, and it has to be on what I call the baseline. You can't be 1 over, it can't be a square root or something like that. All right, let's try another question. All right, what about y equals 7x to the 10th minus 3x squared plus 1 versus y equals square root 7x to the 10th minus 3x squared plus 1. Which one's a polynomial?
The first one.
The first one. Remember, square root, I could write that as what exponent? What's the exponent for square root?
Square.
1/2. Square root's a half.
That's right.
And that is messing me up for being a polynomial because you can only have integer exponents beyond positive integer exponents. Okay, how many zeros might I have?
10.
10. Can I have 0
Yes.
zeros? Because
Even.
number. Good, good. All right, do you have
Is that does it have to be the leading coefficient?
Yes, the
that
degree always comes from the term with the highest power.
But the one where you're talking about, could there be any zeros? Does that have to come from the leading coefficient also?
Not coefficient, leading
The
exponent.
leading exponent also?
Yes, yes.
Okay.
If it's an even degree, this is a 10th degree, then it might have no real zeros,
Right.
because the whole thing could be up above the x-axis. Have I answered your question yet? Do you have a more specific question?
I do.
Okay, with the polynomials. Let me get through with her first. Go ahead. There was something in there that confused you on polynomials. I want to make sure I got that straight.
I got something.
Yeah, finding a polynomial function just by the zeros and the degree.
Okay, so how do you find polynomial function given zeros and the degree? Okay, let's go back. If you know 5 is a zero of some polynomial, what is a factor? If you know 5 is a zero, what's immediately going to be a factor of your polynomial? X minus 5 is going to be a factor. So here's the example. Let's go with a third degree with zeros, -2, 0, and 10. Okay?
Trouble with one of these on WebAssign.
You had trouble with one of these on WebAssign. Good thing we asked then. All right. If -2 is a 0, what is a factor? X plus 2. If 0 is a 0, what is a factor?
X.
Okay, and if you wanted to, you could write x minus 0, but that still comes out to be x. And if 10 is a 0, what is a factor? X minus 10. Now this represents one polynomial with 3 zeros, and if you multiply that out, you're going to get an x to the third as being your leading coefficient. This represents one polynomial, but there's zillions of polynomials, so you normally put a little a right here to represent there's a zillion polynomials with those zeros. If you are given a point that this polynomial also goes through, then you could substitute in the x and y values and solve for the a. Okay, now let's go back and get more specific on your question. What can I help you with on this problem?
Yeah, that on WebAssign. Apparently it won't take that answer.
What, you had to write out your polynomial?
The one I had.
If you had to write it out like this, you probably had to be sure to put little times marks in between.
I tried that and it still came out as cannot understand or...
Cannot understand, so that meant you were typing it in wrong.
The one I had said x, like I had to do x minus 4 times x minus 4 times, it was like 3x to the third or something like that. And I was just going to put x minus 4 squared, but it wouldn't let me do it. I had to do it x minus 4 parentheses multiply
X minus 4, and then it took it.
Yeah.
Probably should have taken the squared, but I don't know why it didn't. After this is over, I'm going to look at your WebAssign and see exactly what you were talking about. But it should take it, if you're doing a times and you're doing times in between each of these, it should be taking it. All right, let's go with you had a question about polynomials. What was yours?
Can you give an example for each M behavior?
In behavior?
Yeah, just like...
Okay. Polynomial in behavior. All right, somebody help me. If I have a polynomial whatever's down here, if n is odd, this is my leading exponent here, the highest degree is n degree polynomial. So if n is odd, what does that tell you about the ends of the graph, everybody?
Would it be going opposite direction?
Opposite directions. If A is positive, they're going to be going like this. If A is negative, they're going to be going like this. So the example is, suppose you have y equals 3x to the 5th odd plus 7x squared plus 1. The thing that we know is as x gets really big, since that's positive in front of the x to the 5th, it's going to fly off in the direction of positive infinity. And as x gets really small, it's headed in the direction of negative infinity. If n is even, the n's are going to be going the same direction. Going to be both be going up if A is positive. This is A positive. If A is positive. If A is negative, they're both going to be going down. Okay, so the example, like right here, might be y equals 3x to the 10th plus 7x squared plus 1. Okay, so if you're odd degree, the n's have got to go opposite directions. Even degree, they've both got to be going the same direction in behavior. And what it means is that when you're looking at this from miles and miles away, the graph is going to look a little bit like that because you're going to just be seeing the end part because it might do a little something in the middle, but in the end it's going like that. Okay? All right, another question for me.
I was like, okay.
Go
Mine's
ahead.
on WebAssign. I'd have to bring it up.
Okay, we'll do that tomorrow. What's yours?
All mine's on the website.
Okay, do you remember the specific question?
Yeah.
Tell me. You programmed it in your phone?
Yeah.
High tech.
Mine was in 3.6. It was 1, 3, and 6.
Okay. If I pull up WebAssign on the computer, I'm asking will you get it right here? Okay. I want to point out to you that these WebAssign questions are coming right from the textbook, and I want you to know where they are. Okay, nobody looking at my password.
Okay.
What is it?
Yeah.
Dot.
Bunch of dots.
Now I need
I
to go
saw it.
change it. All right, so you said yours was from 3.6? Okay. All right, I'm just going to pull this up to view it. I want to just point out to you this part right here that says 3.6011. This problem is basically the very same problem from your textbook, 3.6.
Number 11.
Number 11. I just want to show it to you. So if you're missing a problem in WebAssign, you need to go back to the book, and what's different is that they used a C equal to 6. They even tell you the only thing that got changed in the problem. The book used C equal to 3. So you have the answer to this, or you have the student solution manual to help you practice the problem out of the book, and then you can go to your WebAssign and work on that.
And the student solution manual, does it work out the problem?
The Student Solutions Manual works out the problem in great detail, but you should always work through it, and when you can't figure it out, then use that to help you locate your mistake and then circle it, and it's in your student pack. Will help you find your mistake and circle it in red so you don't miss it again. But I want to go to the problem you're talking about, which was 3.6 number what?
1.
Oh, number 1. Okay. All right, so basically you're using the factor theorem to determine whether x minus c is a factor. Okay, what does the factor theorem say?
When you make
The remainder is 0, then there's a factor.
Yeah.
Okay, so working with your remainder theorem, if you did the remainder theorem, divide by 6. Use your little synthetic division and divide by 6. If your remainder comes out to be 0, then f of 6 equals 0, which means you found a 0, so x minus 6 would be a factor. All right, let's do number 11 directly from the book. and then we'll probably have to stop here.
Are you gonna leave that up?
Yeah, I'm going to do number 11. F of x is equal to 4x cubed minus 3x squared minus 8x plus 4. Okay, the problem in the textbook says, use the factor theorem to determine if this is a factor. If it is, write it in this factored form. All right, so if we want to know if x minus c, in our case, x minus 3 is a factor, we can just go right. If it's a factor, that means f of 3 equals 0. Remember, it says 0 of the function, and we can just use synthetic division pretty quickly. Divide by 3. I'm doing number 11 right out of the book. So we'll do 4, negative 3, negative 8, 4. Bring down the 4. 4 times 3 is 12. Add. That's at 9. 9 times 3 is 27. Add. What does that give me? Negative 19. 19 times 3 is 3 times 5 is 20, 57, and the remainder is 61. Okay, so that means that f of 3 is not equal to 0. F of 3 is equal to 61. So in the textbook, it says determine is x minus c a factor. So is x minus 3 a factor?
No.
Everybody goes no. What does the instructions say?
Right,
Put
0.
0.
If it's not a factor, enter 0. So that's the way WebAssign had to do it.
When I did it,
Oh, I don't know about 6 though. I don't know if 6 is or not, but for 3 it's not.
And, okay.
Okay.
And with the power functions, check the power function. I had a problem describing the power function.
Describing a power function.
Yeah, because I got through everything else, but I can't tell the power function.
Okay, we're going to pick up there next time with your question. You are first. All right, have a great day, everybody.
'Cause I